Hi everyone, I'm Poulami from Georgia Tech, where I'm a PhD student advised by Professor Moin Qureshi. I'll be talking about LILLIPUT, which focuses on real-time decoding in near-term quantum error correction. This work was done in collaboration with Aditya and Cody from Google. Most promising quantum applications require very low error rates, whereas qubit devices are very noisy with orders of magnitude higher error rates. For example, the average error rate of a qubit is 1% on Google Sycamore. This limits us from running most practical quantum applications today. Quantum error correction can be used to protect quantum information, but it is way more challenging than traditional error correction techniques because we cannot copy qubits, and measuring qubits destroys the quantum information. Instead, in quantum error correction, you encode a logical qubit and distribute the quantum information across several data qubits. Additionally, you have parity qubits that periodically perform parity checks on their neighboring data qubits by executing a particular quantum circuit. This process is called syndrome extraction. So once your qubits are initialized, you extract syndromes and use the parity information or the syndrome bit string to identify or decode errors. The job of a decoder is to use this syndrome bit string with zeros and ones and then figure out if there was an error or not. And if there was an error, where did that error occur? And what was the type of the error? And you repeatedly do this as long as your application is running. And finally, at the end, you measure the data qubits. An uncorrectable error leads to a logical error. So quantum error correction protects quantum information at the expense of the increased redundancy by periodically tracking and correcting errors. As quantum error correction is essential for many applications, demonstration of small surface codes is an important step for the quantum community. A small surface code lattice looks something like this. The white qubits are the data qubits, whereas you see two different types of parity qubits. The red patches here are the X stabilizers, whereas the blue ones are the Z stabilizers. Any error on a data qubit is detected by its adjacent stabilizers. For instance, if you have a bit flip error or an X error on this qubit, it will be detected by the adjacent Z stabilizer and parity qubit A will flip. Whereas if there is a phase flip or a Z error on the same qubit, it will be detected by the adjacent X stabilizer and parity qubit B will flip. This is a surface code of distance 3, which means it can correct error chains of up to length 1. To tolerate more errors, the redundancy or the code distance must be increased. We are interested in surface codes because they are widely regarded as the most promising quantum error correction candidate, and their demonstration is a significant milestone in quantum computing. The performance of a decoder is very crucial for quantum error correction because decoders must accurately detect errors in real time to prevent any accumulation of errors and occurrence of logical failure. Typically, syndrome extraction instructions are sent from the control logic, and the syndrome obtained from the qubits is then sent to software decoders running on CPUs. However, software decoders are too slow for real-time decoding. Note that here we are dealing with a syndrome extraction cycle time in the order of a microsecond for existing superconducting quantum processors like Google Sycamore. In most of these systems, the qubits reside at a few millikelvins temperature domain inside a cryogenic refrigerator, and sending out the information from the qubits to the readout logic and from the readout logic to the general purpose machines at room temperature, and then running the software decoder is way too constrained to be done within a single microsecond. Therefore, there is a recent paradigm shift towards using hardware decoders for improving the decoding latency. Hardware decoders are fast, but they sacrifice accuracy. Moreover, they use ASICs or rely on emerging technologies such as superconducting logic, making them very expensive and impractical given the very limited number of quantum computers that are being built today. Remember, we are not making millions of quantum computers in the near term to make ASICs a viable solution. Therefore, existing decoding solutions are inadequate or impractical for real-time decoding in the near term. Our goal is to design a decoder for practical adoption in the near-term quantum error correction studies, and we propose LILLIPUT. Our key insight is that for small surface codes, we don't really need ASICs or software decoders to decode syndromes on the fly as they arrive. Instead, we can simply look up from a table. This table is indexed by the syndrome information, and its entry provides the error assignments for the data qubits. LILLIPUT has low latency, low cost, and high accuracy. Moreover, it fits on off-the-shelf FPGAs, which allows seamless integration with existing systems, because FPGAs are already being used to implement the control and readout logic for current quantum computers. Now let's walk through the different features and implementation details of LILLIPUT. First of all, decoding is about identifying if an error happened in a cycle or not, and then figuring out what was the type of the error and on which qubit did it occur if there was an error in a cycle. LILLIPUT produces error detection events by performing XOR operation between the syndromes from two consecutive cycles to identify if there was an error or not in a given cycle. To understand this, let's take an example. Suppose in the first cycle there is no error. And for simplicity, let's only look at the X stabilizers. Measuring these stabilizers gives us all zeros. But now, in the second cycle, let's say qubit A encounters a Z error. This causes the adjacent stabilizers to flip, and reading the X stabilizers produce 0, 1, 1, 0. Moving on to the next cycle, suppose there is no error. So we will again measure the stabilizers as 0, 1, 1, 0. And finally, let's say in the next cycle, you have a Z error on this qubit B. This will again cause its adjacent X stabilizers to flip, and reading the stabilizers produces syndrome 1, 0, 1, 0. To detect if an error happened in each cycle, LILLIPUT compares the stabilizer measurements from the current cycle with the stabilizer measurement from the previous cycle. And as you can see here, by doing XOR operations, the error detection events can now currently detect the occurrence of an error in those specific cycles. In hardware, LILLIPUT uses FIFOs and XOR operations to produce these error detection events. Decoders must handle multiple sources of errors. To understand this, let's recollect the steps in quantum error correction. First, errors can accumulate on the data qubits. Second, syndrome extraction uses gate operations, and those gate operations can fail. Third, parity qubit measurements or the readout operations can fail. And finally, at the end, measurement of the data qubits can encounter errors as well. For high accuracy, a decoder must be able to tolerate all these errors. Now let's try to understand how these errors manifest and how LILLIPUT tackles them. First of all, errors on data qubits, they cause error detection events in space. Note this usual convention in quantum error correction. This is a decoding graph representation. Here each node is a parity qubit and each edge denotes a data qubit. And we try to match the erroneous nodes or the non-zero parity qubits and assign errors on the edges or the data qubits. Gate errors during syndrome extraction lead to detection events that are spread out in both space and time, that is across multiple rounds, as you see here. Readout errors on parity qubits lead to detection events spread out in the time domain. LILLIPUT decodes multiple syndrome rounds together to tackle these errors. And finally, to deal with errors in the logical measurement, we convert it to a syndrome and compare it with the boundary round syndrome. Thus, LILLIPUT can handle errors in any operation in the quantum hardware. For the operations, LILLIPUT prepares the lookup tables offline by running the software minimum weight perfect matching decoder and performs online or real-time decoding during the actual experiments. It runs the minimum weight perfect matching decoder on all possible detection events and then prepares the lookup table data. LILLIPUT uses a sliding window which slides forward as the error events arrive in each cycle. This streaming mode accounts for events that cross the window boundaries. For error assignments, LILLIPUT finds the best matching that neutralizes all the error events within the current window, but only assigns errors to the oldest round. For instance, let's say we have these error detection events. It's time-like, but it cannot really be captured by the current window because the next round is not yet visible. If we simply consider the best match within the current window and assign errors to any round, we will incorrectly match this event to the boundary. And so assigning errors to the oldest rounds avoids such premature matching. Moreover, we must keep a track of the last assigned errors to prevent inaccurate matchings. For example, if we look at this current window, it represents this space-time-like error which gets matched in this manner. But now, once the window proceeds forward, if we do not have a track of the prior neutralized events, we would be again incorrectly matching this event to the boundary. To prevent such inaccurate matchings, LILLIPUT stores a state information within the lookup table entries themselves. Overall, LILLIPUT maintains error logs and internal state information to accurately track errors. Now, although lookup table decoders are simple and impressive, but they have their own challenges. Their memory complexity grows exponentially with the size of the code and the number of syndrome rounds used for decoding. So how do we reduce the memory complexity? To understand this, let's take a look at the table sizes. Suppose we have this distance 3 surface code and we are only interested in one of the tables. Let's consider only a single round of syndrome. We have 4 bits of syndrome and each entry comprises of 9 bits of error assignment data because there are 9 data qubits and 4 bits of state information required for the decoder operations. So we will need a table with 16 entries and 13 bits per entry. But now, if we want to design the lookup tables for a distance 3 with 2 rounds of syndrome, we will have 4 plus 4 or 8 bits for an error detection event and 13 bits per entry, which increases the table size to a table with 256 entries and 13 bits per entry. Now, if we increase the code distance, the size of the table grows rapidly from 832 bytes to 148 megabytes. Our goal is to reduce this memory complexity, and our insight is that not all error events are equally likely. For instance, if we look at the Hamming weight of the memory addresses accessed over 1 million trials, for a distance 3 decoder using 2 syndrome rounds for decoding, we observe that addresses with large Hamming weights such as 7 or 8 are seldom accessed. Moreover, error detection events occurring with moderate Hamming weights anyway leads to uncorrectable faults and appear with probability less than the logical error rate. So, We only need to have some selective entries in the lookup tables and not all entries. Additionally, let's take a look at this distance 3 code. Although you have these 9 data qubits for error assignments, we can only assign up to 1 error because that's a limitation of a distance 3 code, which means the lookup table entries themselves store sparse data and are compressible. So, we propose compressed lookup tables that only stores selective entries and compresses the data entries themselves. Now let's look at the performance of LILLIPUT. We use Monte Carlo simulations to study LILLIPUT in the context of rotated surface codes. Here is an outline of the framework. We consider a phenomenological noise model that can account for errors in both data and parity qubits. We use a Verilog implementation to target off-the-shelf Intel FPGAs. Here are some results for accuracy for distance 3 with 2 syndrome rounds for decoding. The logical error rate decreases exponentially, which is expected. And as we can see, the compressed lookup tables have negligible impact on the accuracy because most of the decoding requests can still be serviced despite the compression. Note that LILLIPUT is reconfigurable and scalable, which means it can be used to study various decoder configurations. For more results, please refer to the paper. The latency and hardware complexity of a decoder depends on its configuration. It increases with the number of decoding rounds and code distance. The latency is within 42 nanoseconds for LILLIPUT, which is about 24 times faster than the 1 microsecond target latency. The logic utilization is within 7% for off-the-shelf FPGAs, which leaves sufficient room for implementation of control and readout logic. In the baseline, the memory required for these decoder configurations exceed the on-chip memory capacity of the FPGAs, whereas with compressed lookup tables, they can now fit on-chip as the memory capacity can be reduced by up to 107x. These factors make LILLIPUT a lightweight and low-cost decoding solution for practical adoption in the near term. To conclude, quantum error correction is necessary to run most practical quantum applications. And demonstration of surface codes is a significant milestone in quantum computing. We present LILLIPUT, a practical real-time decoder for near-term quantum error correction. It requires less than 7% logic on FPGAs and up to 42 nanoseconds of decoding latency, which is about 24 times lower than the target latency. And we improve the scalability of LILLIPUT by using compressed tables and reduce the memory required by up to 107x. Thank you.